about dynamics of circular motion.
Yes, sir.
Right. Right. So in dynamics of circular motion, we saw that when we apply the concept of Newton's second law, that net force is equal to mass into acceleration. Depending on the type of circular motion, for uniform circular motion, the acceleration is purely the centripetal acceleration. So the net force so the magnitude of the force becomes mv square by r or m omega square r, and it's a centripetal force. It's pointing towards the center. Whereas in case of non-uniform circular motion, the acceleration is the sum of centripetal acceleration and tangential acceleration. So accordingly, the net force also has two components.
That is m omega square r, no?
Yes. Which one?
Left side. F net force is equal to
mv square by r, which is the same thing as m omega square r.
Yeah.
Right? Because centripetal acceleration, it has a magnitude of omega square r, which is the same thing as v square by r.
Yes, sir.
Right? Because v is equal to r omega. This net force is also now having the two components, centripetal and tangential. Because now we understand here that tangential acceleration is radius into angular acceleration or rate of change of speed dv by dt. Okay, so these kind of things come into play. So let's look at another example of application of these concepts. Okay, so this is a hemispherical. Just a second, I'll share the page. It's a hemispherical surface of radius of curvature now a person of mass 50 kgs is running at a uniform speed of v naught equal to 9 kilometers per hour on the surface. Calculate the normal reaction, take g as 10 meters per second square, and the net friction on his shoes. So both of these we have to calculate initially. As functions of theta. And then the third part, calculate the maximum and minimum values of normal reaction and friction for the motion on the surface. So begin by making the free body diagram of the person. We'll discuss. Okay. Yes, Vedant, your conclusion is correct. Okay, so the net force should be towards the center because it's a uniform circular motion. So the first thing to understand here that the motion is a uniform circular motion because he is running at constant speed. So the acceleration is equal to centripetal acceleration, which is V naught squared by R towards the center. So that becomes the important thing when we make the free body diagram. At some general angular position, so we'll see that the forces acting on his body are the weight, the normal reaction that the ground applies, and to counter the effect of mg sine theta, he'll have to generate a friction in this direction on his feet. That is the static friction acting on his feet, assuming that he's not slipping. So his feet are gripping the ground and there's a static friction acting on it. And this is such that, so these are the forces acting. And he's moving at constant speed V naught. So he has a centripetal acceleration in this direction. But tangential acceleration is 0. Yes, exactly. In the second part, he'll have to sort of, brake using friction to prevent mg sine theta from creating acceleration. Here mg sin theta has a tendency to create deceleration. So when we break the forces into components, you can see that this mg sin theta, it tends to create a tangential deceleration. So to prevent that from happening, he has to generate the friction on his feet in this direction so that so because tangential acceleration is zero, so static friction has to balance mg sin theta. And centripetal acceleration is v naught square by r. So mg cos theta minus n, that is the net centripetal force, has to be equal to mv naught square by r. So normal reaction is like this. Okay. Now, if you also consider the motion in the second part, so when he's here, you will see that this time he'll have to generate static friction like this, but same thing will apply here also. Only it's opposite in terms of the direction of velocity. So in both these cases, it's the same equations that apply. So in general, you can see static friction is 500 sine theta, and normal reaction now this V naught in general, this is a normal reaction. So hope this is clear. Make a note of this and also come to the third part of the question. So this is the answer for the first part, the normal reaction as a function of theta. This is the second part, the static friction as a function of theta on his feet.
Sir, what is R in this case?
What is
R.
R is the radius of curvature of the surface, and that is equal to 10 meters given in the question.
Yes, sir.
Understood? So in the diagram, you can see that he's sort of running on this kind of, you can say mound, or which is basically a hemispherical rough surface. It has the center of curvature here. It has a perfectly spherical shape, and the radius of curvature is given as 10 meters. So we have used that value here in this calculation. You'll see in this part when we are calculating mv square by r.
Yes, sir.
So we've used the fact that the mass of the person is given to us as 50 kg. The radius of curvature of the surface is given as 10 meters. V naught is the constant speed at which he is running, 9 kilometers per hour, and we have taken the value g as 10. Okay, so these are the general values that we have used. Okay. Now for the third part, you have to just calculate the maximum and minimum values of this. So from these equations, you can see that since n is equal to 500 cos theta minus 31.25, or mg cos theta minus mv naught square by r. So when is n maximum? When cos theta is maximum? So that is when it's 1. So maximum value is 500 minus 31.25, or mg minus mv naught square by r. So this is how much now? 500 minus 31. So we become 468.75. But this will be at theta equal to 0, or the topmost point. Say, call that E. Okay, so E is this point. Whereas n's minimum value will be 500 cos 30 degrees. Whatever this comes out to be finally. So this minimum value will occur at theta equal to 30 degrees. So let's say those 2 points are B and C. So B is this point here. C is the symmetrical point here. So these are the maximum and minimum values of the normal contact force. Now similarly, you work out for friction also.
Sir,
Yes.
sir, for normal minimum means the minimum normal reaction.
Yes,
Why are we taking theta equal to 30 degrees? Why not 90?
because the surface is that way, na, beta. It's not like you're seeing na, the original diagram, the surface is only between the points B and C.
Yes, sir.
Okay, so the range of theta you can say is from 30 degrees on this side to 30 degrees on that side. Okay?
Oh, okay, sir. Got it.
It's not a complete hemisphere, it's a part of a hemisphere. You know?
Yes, sir. Got it.
Okay, so what about the maximum minimum of friction? Have you worked it out? Friction in general is mg sine theta. So again, the range of theta is between 0 and 30 degrees now. So it will be minimum when theta is 0. That is at the topmost point. So theta is only ranging between 0 and 30 degrees. Okay, so
0 and
maximum friction will be mg sine 30 or mg by 2, or in this case 250 newtons. This will be at theta equal to 30 degrees. That is B or C, both these points. Whereas minimum friction will be 0. This will be at theta equal to 0 or at the point E, the top of the surface. So according to where he is on the hemispherical mound, which point on the mound he is while he is running up or downhill, uphill or downhill, whatever, he has to generate a certain amount of friction on his feet to prevent slipping and maintain the constant speed. So the range of that friction is like this.
So we're done writing.
Done, no? Okay.
Yes, sir.
Sir.
Okay, so hope this concept is clear.
Yes,
Sir.
sir.
You will find some questions in HC Verma as well as your module also based on these all types of applications of dynamics of circular motion. Now we move on to a very important concept. Yes. Yes,
Sir,
tell me.
why are we taking that?
Why are we taking?
Sir, why are we taking the normal reaction to be maximum at theta equal to 0 degrees only?
Because see the formula for normal reaction that you got, that formula is what it is, mg cos theta minus v square by r, no?
Yes, sir.
Understood, no? So cos theta is what type of function? As you're varying your position from B to C, as you're going uphill like that from B
Yes, sir.
to A and then downhill from A to C. Okay, what is varying basically? Theta is varying. Baki terms to वहाँ पे constant है. That whole expression mg cos theta minus mv square by r. The two things which are the only thing which is varying is theta. Na? Everything else is constant.
Sir.
Okay, understood, na? So wherever
Yes,
cos
sir.
theta is maximum, your n will become maximum, and wherever cos theta is minimum, your n will become minimum. So for that entire journey from B to C, where is cos theta maximum? Where theta is 0, that is at the topmost point.
So, sir,
Cos
why it is changing at for friction?
Why is?
Why is the theta becoming 30 degrees for maximum friction?
Because again, see the expression for friction that you got. You got mg sine theta, na beta?
Yes, sir.
So at any given theta, how much friction is required? It's like an instantaneous value of friction required when your instantaneous position is theta. So that depends on sine theta. No? Now, what type of function sine theta is? Sine theta is a function where as theta increases, sine theta increases. No?
Yes, sir.
So minimum value of sine theta will be for minimum value of theta, which is 0. And maximum value of sine theta will be for maximum value of theta, which is at theta equal to 30 degrees.
Yes, sir. Yes, sir. Got it.
So if you just visualize how sine theta or cos theta's graph varies, no? Then you are more clear about this. Okay. Okay, now we move on to another very important part of dynamics of circular motion. So we'll see the concept of the free body diagram of a body in a rotating frame. That is inside a frame in circular motion. And the concept of something you would have heard of, centrifugal force.
Yes, sir.
Okay. So centrifugal force is that type of force which acts on any body which is inside a frame which is taking a circular motion, such that that body tends to be pushed radially outwards. Example, you are sitting inside a car which takes a sharp circular bend. Your own body and all objects inside the car are kind of thrust radially outwards. So if you take a turn at a high speed, for example, without wearing a seat belt, you can even get displaced from your seat slightly because of that strong amount of centrifugal force.
Yes, sir.
Just like you had learned about pseudo force in non-inertial frame or accelerated frame earlier. So an example of that being just like when you are sitting or standing inside a vehicle which is suddenly accelerating forward, your body is pushed backwards. Or if it suddenly brakes, your body is pushed forwards. So you experience a pseudo force opposite to the acceleration vector. So like that, you have centrifugal force, which is basically a pseudo force, which is opposite to the centripetal acceleration vector. So let's understand this. So the example we will use to understand this is like this one, which I'm showing. So imagine you have like a wooden disc sort of platform. And it has a fixed axis and is rotating about this axis with some angular speed omega naught, uniform angular speed. So we have a wooden disc which is rotating like this. Okay. Now imagine also on this disc you have a particle which is at a distance r on the surface and is of mass m. So this is a rough surface. The particle P placed on the rough surface of the rotating disk is at rest with respect to the surface. Is at rest with respect to the surface. That is, it does not slip. So we will make its FBD in the ground frame or the inertial frame attached to the ground. And again, with respect to the frame of the disk, which is basically a rotating frame. And show all the forces acting on it. So before we come to centrifugal force in the second part, the free body diagram in the rotating frame, I want you to quickly work out the first part yourself, that make the free body diagram in the ground frame and calculate the forces acting on the body. Okay, what all forces are acting and how much are their magnitudes. In terms of these given quantities, that is the mass of the particle, m, the angular speed of the rotating disk, omega naught, and the position of the particle with respect to the axis of rotation, which is at a distance of r. So in terms of these quantities, okay, just work this out.
So done.
Yeah. So what are the forces which you are getting in the free body diagram?
So the weight, normal,
Yes.
normal,
Weight, then
normal reaction,
Normal reaction.
yes, normal
Yeah.
reaction
friction,
Yeah.
and friction. Very good. So this is the axis of which the rotation is happening. So when we make the FBD with respect to inertial frame, So in the inertial frame, we observe that the particle is in what type of motion? Uniform circular motion. Okay. With an angular speed omega and radius omega naught and radius r or whatever. Okay. So it has a centripetal acceleration. So which is the centripetal force in the free body diagram now? Right. Which is the centripetal force, people?
Friction.
Yes, very good. Friction is the centripetal force. So friction, static friction is the centripetal force, or it provides the centripetal acceleration. So we have normal reaction balances mg, and static friction provides the centripetal acceleration.
Sir, so friction is like basically acting as a supporter. It is like supporting that.
Friction is acting as a
It is like acting. It is like it is centripetal. It is accelerating that centripetal
yes,
acceleration
exactly. It is
only.
providing the centripetal acceleration. So we say it is a centripetal force because it points towards the center. Correct. So we see the top view. Yeah, Vedant, to answer your question also, okay. The tendency to slip is radially outwards actually. So friction acts in the opposite direction. So as we are seeing this from the ground frame, okay, this particle is at any point of time having a speed v naught in this direction, the tangential direction of this. Okay. So the force that prevents the body from slipping with respect to the surface, because see, if it is not slipping, the next moment this velocity has to turn and become like this now. So which force
Yes,
has to provide that centripetal acceleration? It is the friction.
friction.
Okay, yeah, and weight and normal reaction lie in the perpendicular plane, so they don't affect the circular motion, they just balance each other. Okay, so this static friction acts in the centripetal direction always, pointing towards the center. At any instant. So this is the analysis in the inertial frame.
Sir,
Yes.
the friction can act in the outward direction also.
No, friction, why will it act in the outward direction? You have to understand that. No? Is there any, see, friction always acts in such a way that it prevents slipping. So if it acts in the outward direction, instead of preventing slipping, it will be creating slipping. No?
Sir, sir,
Understand?
the force which is acting in out that particle will be the centrifugal force now.
But that is when we come to the rotating frame. Understood? No?
Yeah.
In the inertial frame in the FBD that we have made so far, okay, there is actually no force acting radially outwards. But what is happening is that the velocity vector is continuously turning now because it's in circular motion. The velocity vector has to keep turning. If the particle has to remain at rest with respect to the surface, if the velocity vector fails to turn, then the particle will start slipping. So friction has to act in such a way that it prevents slipping by keeping it in circular path, by making the velocity vector turn. So when a velocity vector is turning like this, what kind of acceleration a body has? It has centripetal acceleration. So to prevent slipping, friction has to act in which direction? In the centripetal direction. Is it clear?
Yeah, sir. But sir, friction can act as a driving force also.
As a
Driving force.
no, but in this case, it's a uniform circular motion, no, beta?
Oh, right, sir.
There is no tangential acceleration. Yeah, like initially when the platform would have been at rest, to bring it to this angular speed of omega naught, then friction would have had a tangential component also. No, but now we are assuming it's already achieved that angular speed omega naught, and it's moving at uniform angular speed. Got it now?
Yes, sir. Got it.
Okay. So now when we come to the rotating frame, we will have to introduce the concept of centrifugal force. So let's look at this now. Free body diagram with respect to the rotating frame of the disk. Okay, so the rotating frame of the disk is, it is a non-inertial frame. So any body in a rotating frame, which is a type of a non-inertial frame, experiences a centrifugal force. Which is a type of a pseudo force. Just a second, I'll share the file. Yeah. So which is a type of pseudo force given by the relation of this. So centrifugal force has a magnitude r is the perpendicular distance of the body from the axis of rotation. So the direction of centrifugal force is opposite to the centripetal acceleration, or radially outwards. It is along r cap. Okay. So you can also understand this with a comparison. If we are in a non-inertial frame like this, then any particle in this non-inertial frame experiences pseudo force. Like this. Okay. So like that, if we are in a rotating frame, which is rotating at an angular speed omega, then any particle in such a frame experiences centrifugal force radially outwards. particles. So when we make the free body diagram of a body or a particle in a rotating frame which has an angular speed omega, then we have to compensate for the rotation of the frame by taking into account a pseudo force which acts on the body or particle in the radially outward direction, and its magnitude is m omega square r.
So can you scroll up?
Sorry, come again?
Can you scroll up?
Yeah, I showed up.
Around frame part.
Okay, now Vedant, to answer the question you sent in text message, okay, centrifugal force and opposite to centripetal force. See, the thing is when we make the free body diagram in the rotating frame, in that frame the body is going to be at rest. It's not going to be moving in circular motion. So there is no centripetal acceleration. Okay, but there is a pseudo force which is acting radially outwards. So that is a contrast that we'll see of the free body diagram with respect to the one in part 1, where we are in the ground frame. So we are seeing the particle having a centripetal acceleration. Okay. Whereas when we make the FBD in the second part, in with respect to the frame of the wooden surface which is rotating at omega, in that frame the particle does not have any centripetal acceleration because it's not in motion force, a pseudo force called the centrifugal force acting on it, which is radially outwards. So that force will give it a tendency to slip, and to prevent it from slipping, friction has to act opposite. Okay, so see now when we make the free body diagram in the
Can you wait
rotating,
for a second?
okay, okay,
Yes, sir.
okay. So now when we make the free body diagram with respect to the rotating frame of the disk. Okay, so imagine we are on that disk which is rotating at omega. So with respect to us, we see the particle is at rest. In this frame. But when we make its FPD, we have to understand that we are in a rotating frame of angular speed omega. So the particle being at a radial distance of r, it is experiencing a centrifugal force radially outwards. So this centrifugal force now, it gives it a tendency to slip. Okay. And to prevent that slipping from occurring now, friction acts. Static friction acts to prevent slipping. So static friction balances the centrifugal force. Hence the magnitude of static friction is m omega naught square r, and normal reaction balances mg. So when we see the top view, exactly, friction acts in the centripetal direction to prevent the slipping. The tendency of slipping is coming because of centrifugal force when we look at it in the non-inertial fluid or in the rotating fluid.
Yes, sir.
What's RF in the diagram? First,
Sorry, come again, Vita.
RF in the diagram. Second one,
I didn't understand.
RF you're in the second diagram.
Second diagram is the top view. Okay, so r is the distance of the particle from the axis of
So
rotation.
no, the free body diagram. Second one.
In the FBD, yeah, r is the distance of that particle from the axis of rotation.
RF.
Capital R, it is the
RF.
perpendicular
Written the
rotating
RF.
frame. RF stands for rotating frame. Rotating frame. So we're making the FBD in the rotating frame. Okay, so hope this is clear, people.
Yes, sir.
Okay, so with this, we'll conclude today's session here. Now, hope you people have been working out questions from HC Verma for circular motion. After today's lecture, please complete up to question 27 from HC Verma. Okay.
Okay, sir.
Next lecture, we will begin the lecture with discussion of few of the questions from HC Verma. Okay, so please do HC Verma exercise problems. From the chapter of circular motion. 1 to 27 we'll discuss in the next lecture, and then after finishing the discussion of these questions, we will move on to the next part of circular motion, which is vertical circular motion, where we'll have to
Will you
use,
discuss the major test questions also?
yeah, that also, but I think there will be a separate session for discussion of major test. Okay, after the 3 papers are done, you will have
Okay. Okay. Sir.
in your schedule only, you'll have a additional session for that. Okay, so how much of work by energy you have completed?
We're done.
So what?
Sir, we
So
are done with the chapter work power energy.
We are done now. Okay, so conservation of
Completed
mechanical
yes,
energy, all that is clear, because we'll be using that in vertical circular motion, which will start after discussion of these questions from HCB. Okay.
Okay, sir.
Okay, so that's it for today's session, people. Thanks for
Thank
attending.
you,
and
sir.
look forward
Bye.
to- Bye.
Thank you, sir. Bye.
Thank you, sir.